I'm just gonna talk about the concept of garbage collection. Let's have a stack and a heap, and let's have like a top level view. Let's say you got a bunch of objects in the heap, and some of the objects are referencing some of the other objects.
All right.
And then on the stack, you have these frames with variables. Some of the variables are like pointing to these heap objects. So maybe you have something like this going on. So what we're going to talk about is, we called it faux GC last time. Another term for it is tracing GC.
What is trace?
Tracing GC. Both of these terms I'm using to mean the same thing, and the reason it's called tracing GC is because the algorithm used to do the GC, do the garbage collection, is a tracing algorithm, and it actually comes directly from graph theory. There's a part of computer science that is graph theory. There's a bunch of research in graph theory algorithms. A graph is represented by a bunch of nodes, which look like little circles. The circles are nodes. And you can have connections between the circles. These are called edges. So the little arrows, they're called edges. And the edges can either be unidirectional, which in this case it is, or they can be bidirectional, if it goes both ways. If it's bidirectional, usually you don't even bother writing the arrow because it's implied it's both ways. In our scenario, it is going to be unidirectional because a reference is unidirectional. Like this variable points to this heap object. This heap object does not point back to the variable. The heap object knows nothing about this variable. So this algorithm that does this garbage collection comes straight out of the graph theory repertoire, and it's the reachability problem. The reachability problem is this. If I start from this node, is it possible to reach this node by traveling the edges? So you might imagine a more complex graph. Is it possible to reach this node here from this node? In this case, yes, because I can go blah, 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 and I reach this node. Is it possible to reach this node from this node? No, because this node has no outgoing edges. It can't go anywhere.
So do you have to traverse the graph in order to calculate whether you can reach a node, or there are other ways to do it?
Yeah, that's what you do. I believe you're familiar with binary tree traversal, right? Or just tree traversal in general. A graph traversal is not really any different from a tree traversal. You have a way of accessing your children or the neighbors that you're able to reach that are direct neighbors, and you just go to them to recursively traverse the whole graph until you either find that you reach the thing you're wanting to reach or you don't. So yeah, basically that's what you do. You recurse. Just pretend this was a tree. Like this is a tree actually in this case.
Okay.
The one difference between trees and graphs is graphs are allowed to have cycles. So if I add a cycle in this graph, or two cycles, this is not a valid tree anymore because trees must not have cycles, but a graph is allowed to have cycles. So basically, this reachability algorithm is what is used to do garbage collection for a situation like this with a stack and the heap. The most famous algorithm for garbage collection is called mark and sweep. Step 1 of mark and sweep. For each heap object, mark as unvisited. This is the initialization step. And then we're going to traverse it and then mark stuff as visited as we go. And then we're going to, for each global variable or variable on the stack, start a graph traversal marking each visited node as visited. So for example, we're going to start from A var and B var and start traversing the graph, right? Each one as you visited, we're going to mark that node as visited. And then finally, the third step is for each unvisited node, or I should say heap object. That's what the nodes are. you can free the memory so that other things can use that memory now.
So for any object in the heap, if nothing refer to it and it cannot be reached by this algorithm, so then we can just free it.
Exactly. So let's do it on this graph. First, we're gonna do step 1, which is mark each one as unvisited. I'm gonna put a little parenthesis and put a U next to each one, right, for unvisited. And then for each global variable, we don't have a global stack, but I could. Maybe this one is a global stack, and the global variables go on the global stack. I don't know. Or the global variable could go on a different place than the stack. It doesn't matter. But we're just gonna work with these two variables that are on the stack. So start with a var. We're gonna traverse to this guy, and then because we were able to reach this guy, this becomes visited. We're here and we need to visit its 2 neighbors. So we visit this neighbor here, and this guy becomes visited. And then depends on if you're doing a depth first or a breadth first, you might visit this in a different order. But here, let's do a depth first, and then we're gonna follow this edge here. And then so we visit this one, and this becomes visited. We already visited everything, so maybe this example weren't super great, but the next thing we're gonna do is do the same thing starting from bvar. We're gonna first see this guy, and bvar is gonna see that it's already been visited and just jump out because if it was visited, then it would have visited its neighbors as well in the previous round. So there's nothing for this one to do. Since we haven't seen a case where there's actually dangling objects, let's make an example where, like in this case,
can't free anything.
Yeah, in this case, everything was visited. So step 3 has nothing to do. There are no unvisited heap objects. Let's make a separate example. So in this case, if we did this, it will still visit everything. But let's say B. We got done with this function call, and this frame got destroyed.
Okay.
B doesn't exist anymore. So now if we do this algorithm, we're gonna mark every object unvisited, and then we're gonna start with A and visit this one. So this one is gonna be V. V and U, I'm writing them very, very similarly. Maybe I'll put like a underline under the U's. Okay, and then we're gonna visit this one, and then this is gonna become a V, and that's it. So these 2 ended up being unvisited, and we're gonna free up their resources. And then if this frame also gets destroyed, then you can see that we no longer have any variable starting point. So these are gonna get unvisited, and they'll get reclaimed. The memory get reclaimed for other uses also.
So when do you re-execute this algorithm? Is that like every time a function returns, you just do it?
That's a great question. Before going there though, what's the big O of this algorithm?
By big O, we mean like more stuff in the stack, or like.
Okay.
What is here?
Let's say there's n heap objects in here, maybe m variables on the stack. What do you think the big O of this mark and sweep algorithm is?
So the worst case is, so each time m adds, there's another m, there's gonna be the most n to the power of n, because you don't know how these heap objects are referencing each other. So
one thing to remember though is that if you visit something that's already been visited once, you can actually stop the execution there, and you no longer need to go further.
Oh, so to the most, everything will only be visited once.
Like you mark this, Maybe there's multiple variables that will end up visiting these, but once they visit it, they don't have to do the traversal that's related to them anymore. Maybe because you mark this one, you also mark this one. So you visit this guy, and then you don't have to do this traversal to visit this one anymore.
Wait, so that means that's just mn?
M times n. It's not even m times n. Let's say m was 100. You have a stack that has a lot of variables on it, and n was 10. I think m would have very little impact on the performance, and the n has more impact because at the end of the day, you're traversing those 10 objects, and these 100 variables, most of them are going to go back to the same objects over and over again.
Right.
And the first time they hit something that you already visited, it's stopping. So even though there's many of these, they're not doing that much once the nodes have already been visited. So I actually think it's mostly big O of n. You visit this one, cross, and then the next one is okay. Oh, it's the same one. Visit this one again, and then you visit this one again, and maybe the next one goes here, and then visit this one again. Like most of the 100 is gonna be spent just seeing that you already visited that one.
Gotcha.
Yeah. So I think.
Yeah, that makes sense.
I actually think it's big O of n, and yeah, I mean, this does matter. It matters less. Maybe it's like a m times some constant, but maybe it's like this. Maybe it's like this.
Okay.
It's m times some constant plus n times some constant. But in any case, I'm not sure if I'm totally right on this. So somebody, you can, if I'm wrong, please correct me. Let's just say that it is big O of n. It is at least big O of n. That means if you have a lot of heap objects allocated, it could potentially get expensive, right? Which leads us to the second question. When does this process kick in? What do you think? I can tell you JavaScript does this. Java does this.
We talk about when a function returns, right? We need to recalculate.
Okay, when this function returns, it doesn't do it that often. Like if they did it every time a function returns, it'll be doing that all the time. It'll severely penalize your program, because this is a big O of n operation that's happening all the time. I mean, a lot of times your program is still keeping a lot of the objects, so you're just visiting those objects over and over again, and only reclaiming a small percentage of the objects, and you're doing that all the time. That's not good. They're very lazy about doing this process. As I understand it, they only do this when they have to. When do they determine that they have to do it? When they try to request for more memory, but the system is not willing to give us more memory.
Oh, gotcha. That makes sense.
So I think I ran up against the memory limit for Chrome one time, and when that happens, your environment, it might be your operating system or your browser. In this case, if you're doing JavaScript in the browser, that's Chrome that's making decision about how much memory is too much to give. But there's a threshold. It's not necessarily how much memory your computer physically has. That's because of something called virtual memory. I'm not going to try to dive into that because that's a whole separate topic. But in short, virtual memory is the computer is making your program think there's more available memory than there is. It's giving your program the impression that it has a lot of memory, even bigger than the amount of physical memory you have.
Why does it do that?
Why does it do that? Just make the programmer's job easier. Your program is not the only program that's running on the computer. If the computer was like, I only have 1 gigabyte of physical memory, and I have to run 20 programs. Therefore, I'm going to divide up my physical memory by 20 and give each program only that much, only, 1/20 of the 1 gigabyte that I have. Then
some programs
Yeah,
that much.
the program then have to worry about, oh, how much physical memory do I actually have? And then does it have to, do things differently based on how much actual memory? Because if you're basing it on physical memory, then when the physical memory is used up, you actually can't continue. There's actually no way to add more memory if you're basing it on physical memory. So virtual memory allows your program to ask for more than its share. That way the program doesn't have to worry about the physical limitations of this machine, because you want to write a program that can work on a lot of machines, right? Not just the machines that have a lot of memory. Right?
It's like the air company like oversell the air tickets.
Yeah, yes.
And because
yeah, it's not exactly like that. Maybe we could do another session about virtual memory in the future, but
sure.
but that's the short version of it. But then even despite that, the operating system still places a limit on how much memory you can have. I actually don't know what that threshold is. Maybe I should read more about this. At some point, if you ask for too much, your operating system is going to say, no, you can't have it. And basically, at that point, the garbage collector is time for it to kick in to hopefully reclaim some of the memory that you currently own, so that these objects that we can X out, and we're going to recycle them for use by your own program.
Gotcha.
Before I forget, last time I should have talked about this, but I forgot. And that is one drawback of the ARC, which the mark and sweep scheme fixes this drawback. Your object graph has a cycle in it.
Right.
So when the field assignment happened, remember, we're supposed to increase the reference count, right?
Yep.
This guy's reference count is 2 because it's this arrow plus this arrow, right, from the stack.
Right.
And then this guy's reference count is also 1. So now this stack frame got destroyed because that function is done. We're going to decrease this guy to 1. And now all the reference counts are 1. But these 3 objects are unreachable from the stack.
Oh, okay, gotcha.
They're mutually pointing to each other.
So how does the program that use ARC or the language that use ARC resolve this?
Good question. One way is they prevent you from doing this in the first place. That's one strategy. There's another strategy called weak pointers, which is a pointer that points to the object without increasing its reference count.
Okay.
In the ECMAScript, do you know there's a thing called the weak map?
I heard about it.
Yeah, there's a ECMAScript weak map, which it's just like a map, except the keys are weak references. If you do new weak map, so my map is a new weak map, and then first of all, in a map you can use objects as keys. That's number one. If you've been using just object literals for your dictionary, you might not be used to that, but it is possible to use the object as a key. So that's the key, and then maybe like a value. I'll just put a number, right?
Say the key has to be the same reference on the same object. It can't be like a copy or something, right? It has to be the object.
Yeah.
That's like the object.
it is the object that is the key of this map. Like internally, this is a hash table. It probably looks up the object's memory location, probably uses that as the key, and then it might transform it using a hash function. So this is possible with both the map and the weak map. The difference between the weak map and the map is with the map, if it were an ARC system, which JavaScript is not, but if it were, then with the map, it'll like +1 on the reference count on that object. With a weak map, it will not +1. That's the difference. So the key is a weak reference. So the weak map means keys are weakly referenced. Since JavaScript is not a reference counted language, I'm gonna draw it like a graph. So let's say this is map. This is the map that we have here. And I have obj here. And maybe there's other objects. All of this is the heap. And then we have the stack, which may have some pointers to objects over here. If this was a normal map, not a weak map, then for each key that you use with the map, there would be a pointer to the objects, which means if you run the mark and sweep algorithm, there should be a pointer to this map. As long as the algorithm reaches this map, it'll also reach all the key objects that are used within the map. So basically all the objects that are keys in this map are retained by this map because the map point to them. However, if this were a weak map, that is not true. If it was a weak map, then the system do not track the references that the map has to these objects, which means if this object gets cleaned up, maybe this pointer got removed somehow, this object will get cleaned up. Even though this object is a key in this map, it's gone. And that means implicitly the entry in the map is also gone, which does not break the program because there isn't another place in the program that has this reference to be able to ask your map for this key again.
Okay. So how does it keep track of whether there is another part of the app that's asking for this key after that thing is destroyed?
It doesn't keep track of it. It doesn't keep track of it. It's just impossible. If this object got reclaimed, that's because there are no longer variables on the stack or from any other object that's referencing this one anymore.
Okay. So basically the process of having the map that has which is not a weak map, that was redundant to begin with, because if it's technically impossible, right? So
I see. You're saying why would you ever use not a weak map?
Exactly.
There is a reason to use a non-weak map, which is you can actually iterate the entries of the map.
Oh, gotcha. So weak map cannot do that.
Correct. A weak map cannot iterate through the entries of a map.
Okay, that makes sense. Interesting.
I want to wrap up by just saying, if you have this cycle situation in a mark and sweep algorithm. Okay, so what we're going to do is, if we did the mark and sweep at this point, then all of these guys would be visited, obviously. The problem is if this function was terminated and we destroy this frame, this pointer is gone. What would the mark and sweep algorithm do? Well, it would mark each one of these as unvisited. So these are unvisited. For each variable that's on the stack, we're going to start the traversal. Well, there's no variable to start the traversal with. Our stack is empty. So none of these guys get traversed, and therefore all of them stay unvisited, and we're gonna loop through the untraversed ones and then destroy each one. So basically, the mark and sweep solves this problem. So in a mark and sweep garbage collected programming language, you don't have to worry about having cycles in your objects. And that's kind of a big drawback of the ARC approach. However, I have read recently that Python is an ARC-based language. However, it has some algorithm in there that it uses to remove this kind of cycles automatically. So I want to dig into that. I want to understand how that works.
Okay. So Python is actually using ARC.
Yeah, Python. Yeah, Python uses ARC, which is surprising to me, honestly, because it doesn't feel like an ARC language. Because I looked at ARC languages before, like Swift, Rust, Objective-C, and all of them have these extra stuff that they introduced to cope with this problem, and Python doesn't have that.